record on this computer. All right, let's start this. Okay, so starting off from scratch, like numerical Euler integration, the idea is that it approximates a derivative by a very, very small difference. It's like, imagine like a new value minus an old value, and then you divide it by a certain amount of time. Generally, we want to see how things change against time. This is like more physics-based stuff. It's like we're not worried about other types of derivatives yet. But like generally for the time being, time. Anyway, no.
Nice.
Yeah, for the time being, we'll worry about changes in times. It's easy to think about this way. So the idea is like, say for example, if I want to like solve like a really like elementary one, like dy dt equals 2, you already know that like the solution is like, 2t plus whatever constant. Generally, what we do when we solve differential equations is we start off with this and we give an initial solution, like an initial condition, right? So like, y of 0 equals something, or some particular value to start off with, right? Yeah, so say for example, pick a number. I don't know.
7.
7, yeah, nice number. So you automatically know the solution is 2t plus 7. But the way that like numerical integration works is that it tries to kind of get like a list. So imagine if you have a time like array. So imagine it like 0, 0.1. And so it solves for the y values at each of these times. So 0.2, 0.3, all the way until like, I don't know, however long you want it to run. So say, for example, if I run it to run for 1 second, if you want to call it that. So then like, what it would do is that in its loop, like the way it would compute it is that it takes the amount of time elapsed here. And so it automatically knows that the first value is 7 because that's what you told it. Yeah. Then from here, you can rearrange this. And so you can get, let's see, delta t times dy dt, and then plus the old value. That gets you your new value. Yeah. Just rearrange the same equation. We know this because that's just a time interval between two times. We know dy dt because we gave it, and we know the old value because that's the previous value. And so we just keep adding it on and hopping forward. So from here, you can manually compute it. That's just like, I don't know, 0.1 times 2, 0.2, 0.2 plus 7, 7.2, and then you can see 7.4, and then so on. And then at the end, we'll get like, I think 9. Quick maths.
Quick maths, nice.
Okay, so like the idea is that it recalculates each of these and it hops over to the next one. Yeah. This becomes really efficient, especially when you are solving like more complicated ones. So say if you want to say dy dt is equal to 2t, then you can make it dependent on the time value as well. So it's like 2 times the previous time value. And then like, instead of this, you plug in 2 times the previous time value into this whole business. And then you'd solve it bit by bit. ODE solvers work in a very similar fashion, except that there's a bit of a difference in the sense that you see how here we equally spaced out everything?
Yes,
like as in everything is 0.1. We added all 0.1 again and again.
Yeah.
So what MATLAB does is something pretty smart where it'd be like, okay, so I want to still get the maximum information available, but I don't want to do so many computations. I don't want to do so many calculations, but I want to get the maximum information while getting like, the same amount of info. Yeah. So it kind of does like an optimization. And so what it does is that instead of taking like a time value of these, it could try something like 0, 0.1, 0.3, I don't know, 2.5. And then like it can step it up. It can change it. It can change it to 0.5, for example. It can then go from 1 and then 1 point, and then 2 and then 5 or something. Doesn't matter. But the point is that you notice that the step sizing changes each time.
Yeah.
That's what MATLAB can figure out. And it will work it out practically the same way. And it will just solve from the previous values. So just like this, I can give an initial condition, say, for example, y of 0 equals 0. And so you automatically know that it's like t squared or something. but like, so then you get like that y, you can just solve it again. So 0, and then you get the next value, and you'll like loop over each time, depending
Yes.
on whatever's there given before.
Okay.
Does part make sense so far?
Yes, yes, it does.
Okay, right. So from here, this is basically how we transfer this into code. So the crux of every like ODE solver in MATLAB, first you have like the time span at which you are simulating over. Can't let it go forever, it needs to stop sometime. So say if I made this from 0 to 1, you give it an initial value, so like how we did before, y0 equals 1. As an example, you can change that to whatever you want. And then this cute little line tells us to like actually solve it. The way the syntax works basically is that first, this is a function that defines the differential equation. So this is the whole thing down the bottom. Function works the same way as functions work in any other code, but yeah, it's just like, this is just different syntax. The point is that at the start, you just have at, and the at symbol, and then whatever function you're working with. Second comes your time span, however long you want to simulate for, and then your initial value.
Okay.
Yeah, that's just how the syntax is, and then it will automatically solve it depending on what differential equation you give it, and it will give you t and it'll give you y. And then when you plot it, it just produces the output that you need to. Looks very pretty.
Yeah.
So the way you define the differential equation is exactly as you can see here. So dy dt, so whatever output you want as your derivative is equal to name of function. Doesn't matter what the name of the function is. I could just call it Bob. Doesn't really matter.
Yep.
So Bob and t and y. Cool. So the idea is that like it just takes in t or y as possible inputs, because the derivative normally depends on what y is or t or something along those lines.
Yeah.
You know, like generally when we talk about differential equations, they generally depend on like y and t and stuff like that. Yeah.
Yeah.
Okay. So yeah, here I define the derivative dy dt as 2 times t. So automatically you know that derivative that just solving this is going to be y equals x squared, and then because the initial value is 1, so it's x squared plus 1, and so that's the function that I got up here.
Yeah.
Yep. So that's how this whole business works. I'll send you the code for this by the end, so you no need to work too hard. Just yeah. Okay.
Oh, thank you.
Oh yeah, all good. Okay, so the way it works with higher derivatives, I'll start with higher derivatives and then I'll go into more like general or complicated situations. So say for example, if I want to do like, you know, like a regular like gravity, like 2D gravity, like sort of in the sense that like dy dt equals negative 9.8. 9.8. We're engineers, we say negative 10. Oh yes.
Oh no.
Oh yeah. d squared y dt squared. Second derivative is negative 10. The way that we work with this is like the idea of a state, and you'll be getting into this next year as well in AME 3500. It's an idea called a state, and it's basically like a track of every derivative. So imagine if I create like a new vector. Give me a cool name for something, like a letter or a name.
Ice. Yep.
Ice.
Ice. Yeah.
Okay, probably a letter. A letter would probably be easier because it was naming a variable.
Oh, okay, true. What about just Z? There you
Z.
go. Classic.
Yeah. Okay, so Z is and so I name my state Z, and what it contains is 2 values here, specifically 2 in this because it's a second order. I'll have y, and then I'll have dy dt or y dot, doesn't matter what I call it, but yeah. So I call it y and dy dt. The way I think about this now is that I think about how this pair changes. Okay, and so imagine if it has 2 separate things. Okay, and so what I can say is, so if I take dz dt, is just the derivative of each of these. which is going to be dy dt. And then the bottom here, that's -10 because that's the second derivative.
Yeah.
So the thing that makes this convenient is because the derivative of a state generally is written in terms of itself or some numbers involved. So you notice how z here, the second value has dy dt.
Yeah.
They're the same. And then
yeah.
like the second derivative is just a constant, so we can just throw that number in.
Okay.
Okay. So the easiest way for us to solve this ODE solver is, imagine if we treat, instead of y as just a number or its own function, it could be like an array of functions, which is what that state is. It's like an array of functions.
Oh, okay.
If that makes sense. Yes.
I think that does make sense. Yeah.
So so this way we only need to worry about one derivative because everything it like kind of like depends on itself. So if I were to code this particular thing, this particular situation, and say if I was like dropping a ball, notice with second derivatives we need two initial conditions, an initial position and an initial velocity, right? So we have so y of 0 equals something, and then y dash 0 equals something. So initial position, and then initial velocity. So our initial position at time 0 is, give me a number. Probably positive. Put it.
4.
4. That's a very nice number. What about velocity?
12.
12. Pretty fast. So here it's going up and then going down. So that's a way visually you're imagining it as ball getting thrown up at a velocity of 12 and the height of it is 4 meters. Something like this. This is like the situation that you painted for. Yeah. Okay, so the way now I'm thinking this through is now my initial values, I'll call this, remember that you call the state Z, so I'll call it Z naught. Okay. And I'll call that now the initial values is, remember we have the position and then we have the velocity. So position is 4, and we have 12. How long do you want to run the simulation for? 10 seconds?
Yeah, 10 seconds, that works.
10 seconds sounds good. Okay, right. So we define our time span, initial position, initial values, so position and velocity. So I can make a new little list thingy and say y naught. Yeah, y naught equals 4, and then v naught equals 12. And then like I can just call this y naught and then v naught. This is like kind of just in general better coding practice because you can just sub things in and type it over here. Honestly, a personal preference. I don't really mind. Don't care. I'm not your marker. But yeah. So this is our initial position, initial values that we subbing it in. We got our time span. That's cool. And then now we have to introduce our variable, our derivative thing. So this would be z. So now we're differentiating z against time. So then the way I'm thinking about this is, okay, so what we did is when we differentiate dz dt, should actually write that as my output here, dz dt. Okay, so yeah, okay, so the way I think about this is, let's see. Okay, so imagine y is equal to the first value and then y dot is the second value. Right? You can see that here. The way we defined z was that like the function and its derivative as like the two values. So let me like call it that. It's easy to think about this way. So z, the first value, and then y is equal to z, second value. The better way to do this is first row, all columns. That's what that says. And then second row, all columns. Row, column, row, column. Nice.
Okay.
Okay, and so that's a y dot. Yeah, that's the second one. Yeah. Okay, so we got y and we got y dot. oh, this is also going to be Z over here. And then so this is going to be, I'll use this later. Don't worry. We'll worry about that later. Okay. So now we need to find our second derivative, right? Our second derivative is going to be, okay, so wait. So the derivative of the entire state is going to be y dot, which we already gave it. And then we got the second derivative. So then what I know is that, so I can say y d dot, double dot, equals -10. And so then the derivative of dz dt, like the derivative dz dt, is equal to, it's going to be y dot first and then y double dot. That's the way we pose this. When we differentiate z, we got like each of these dy dt and then d squared y dt squared. Since we already have dy dt, we can just plug that in. So then that y over there, we'll just put, sorry, y dot. And then we also have y double dot. So y d dot. That's as simple as that. So you have the derivative dot and then double dot. The way we wrote it, z is, yeah, that we did y and dy dt. If you really decided to, you could just swap around them, and then so that way this gets swapped around. MATLAB doesn't care, it will solve it the same way. It's just make sure everything is linked and attached properly. General practice though is to do all your lower derivatives higher and then your higher derivatives like down. That way it's easy to think about. So if you have like 0th derivative, this one, and then first derivative, second derivative just steps down. So you can think about everything easier.
Yeah, makes sense.
Okay. All right. So yeah, always put semicolons on things, otherwise the code will just won't shut up. Okay, so all right. So now when I solve this, actually, let me just comment this out for now. Now that I solved this, you just see this output first. Let me just go hide controls. Okay, yep. Okay, so now that I run this, what happened here? Bob must return a column vector. Ah, this is a row vector. This is a row because they did them one beside another. I need to do them as a column. So this automatically makes that a column. Otherwise, what you could do is, this is like a row, but then you can transpose, and the dash does a transpose. It doesn't matter which way you do it.
I didn't know that.
Yeah, so convenient things. Either way, both do the same thing. Okay, so now the way you see Z is they did this as columns. That's kind of dumb, but who cares? Alternatively, I could make this a column and then it would automatically do it the way I want it to. Let me make this a column. And then I think this should work fine as rows. 93, where's this? 115, 13, 13. Is it not? T-span. Okay, never mind. I guess it just doesn't want to work on it. That's cool too.
Oh no.
You do you, code. That's okay. All right, that's fine. Okay, so this is my initial position. This is my initial velocity. And so this is now my new positions after each time, and it'll automatically change velocity accordingly. And so what I can do is now when I plot, I'm plotting only the position, which is the first value in Z, all of this against time. And they gave a time vector as well.
Okay.
I'm not sure. That sounded like I'm not confident. Okay.
Oh no, that was like a, yeah, I think that makes sense.
So alternatively now I can just redefine y and y dot out here. Things that are in functions stay in functions so they don't pop up in your workspace. Notice that y and y dot don't pop up here. If I create them here, then it'll just load them out. So now this is the first row, 4 columns. That's not what I want. I want, I can transpose this because I just don't like looking at stuff like in rows like this. I want to see things horizontally.
Yeah.
That's my personal preference. I don't know about you.
No, I feel that. Yeah. Can relate.
It's like things are personal preferences, but one way is still right.
Yeah,
No,
yeah.
I'm kidding.
Right.
Okay,
So you sure you're not going to get marked down for having something, the different way to what the tutor likes?
to be honest, I don't think they'll care, because as long as you produce the right output, like plots, then they really shouldn't mind.
Okay.
They do mind a bit about style and stuff like that. I don't know about you, but I have like I've grown a little thing that's like an aside at this point, where it's like I like to tab indent everything, where everything like seems perfectly aligned. Oh no, where'd it go? Okay, yeah. And so it's like
Yeah,
everything
okay.
is perfectly aligned, and like like just cleaning up code like that, it just like looks aesthetic in its own way.
Yeah.
That's just like my little thing that I've picked up now. This is
Yeah.
something you might want to try, like when you're cleaning up code and stuff. Anyway,
Okay.
so now I define y and y dot separately outside the function. So now when I run it again, count that out. When I run it again, you'll notice that we got a y dot and a y, and they're both their own. Like I just extracted the columns or rows now.
Okay.
Yeah, so it's the first row, second row, and then all columns. So first row, all columns, second row, every column. And it just does
Yeah.
it for all of them. Yeah. Okay.
Okay.
So then what I'm looking for is only y, how y changes against time. So how y changes against time is just t against y. So t is the x-axis, y is the y-axis. So then when I plot it, it shows the ball falling.
Okay.
And this is exactly what you expect, because the ball goes up a little bit and then it falls down.
Yes. Yeah, it'd be
then,
a war if it just kept going up.
so if I plot as well, so if I hold this on and then plot t and then y dot, hold off again. You don't want it to hold on for too long. And it plots both of them now. This is the derivative. So this is now the constant acceleration, or like, the velocity is constantly decreasing.
Yeah.
And then like, this is the ball like going up and then going down. Notice how the velocity starts off at 12 as well.
Yeah.
So that's how this kind of works. So you think of everything as like states. So this is how you would normally solve like higher order differential equations. You just have like more and more lists of like more stuff's moving down. Another thing I just wanted to go through was like now more so like how do you represent like different states of different variables? So say you have x and y, or if you have x, gamma, height, whatever, like multiple different types of variables that interrelate with each other. That's kind of a doozy for you. And this is like now the challenge of space physics. So let me give you an example. This is not like directly related to any of your assignments. Okay, sort of is. But what I'll do is it wouldn't count as plagiarism or anything like that. I'm just going to take a 2D problem. Okay, and imagine if I have a 2D Earth. Okay, and I have like a weird 2D version of gravity, where if I have a particular point, the acceleration is just going to be like, the same gmm on r squared. And r is the distance like x squared plus y squared. So you have an x distance, you have a y distance. Yeah. And then so, r is like, x squared plus y squared and stuff like that.
Yeah.
Yeah. Okay. So this is the problem I'm going to pose to you. I probably want to keep this in orbit. If I get it to fall towards the center of the Earth, it will just keep falling, and yeah, it will just keep falling. So it would start like breaking down physics because you start dividing by 0. Don't want that.
Yeah.
Okay,
yeah, no, that sounds a bit too funky.
Okay, yeah. So what I'll do is I'll give you an initial situation where my initial position is at, I don't know, 10,000 kilometers. Kilometers, and it's moving upwards at like a certain speed. This way I can give it like an orbit to move around with. Like I'm just picturing in my head. Yeah, so this is like my Earth and stuff.
Yeah.
So
Yeah. Cool.
the way they normally like run this is that they you normally say that m is generally very small. Like I'm sure you've went through a derivation like this in space by now, but like yeah, you would generally write mu on r squared, I think, and you write mu as equal to gm or something like that.
Yeah. Okay.
Have you been through this?
We probably have, but he went very fast and like didn't really say much, so
Fair enough.
I probably
So
missed that. Yep.
yeah, that's okay. So the way that they kind of pose this is that the mass of the object compared to the sun, moon, the earth, gosh, I can't even get my planets right.
Third time lucky.
Oh yeah. Yeah, so it's generally very small compared to the earth or whatever or like body you're orbiting. So you generally neglect that and you just write mu over r squared. Generally you have a negative sign because it's opposite the direction. So positive x is this way, positive y is this way. So generally like the force is going to be opposite those. So it's going to be negative. If you're on negative y, negative x, it's like in the positive x direction. So it's like it's opposite the direction that you deem as positive.
Okay.
I'm pretty sure this is the formula. But when you write this in like a vector form, if r is your vector from the origin to this, that's r. So then the formula for the derivative of how r changes, so I can say dr, the vector, dt, and I can write r as, now this is like similar to how we write z, it's a state. And I can write it as x and I can write it as y. You know, just x and y coordinates.
Okay.
And so they normally write the second derivative dr squared dt's as that's right. This is an a, and so the m's cancel, and so your acceleration is just mu on r squared. That's where that came from, right? So
okay.
yeah, that's right. So the m's cancel, and then you just have a is equal to whatever force this is. This is the magnitude of the force. But when you write it in vector notation, it's just mu over, now it's like, so I can write it as mu over r squared. So it's the same thing as gmm over r squared. The thing is this gm is, this business is gm. And this is generally for Earth, but you can write like a different mu values for different objects. And that stuff is in the textbook. The textbook automatically has values of these.
Yeah.
Because they're all constants, it doesn't matter. Yeah. So I'll call it like GME for now. Over r squared. Okay. And then like all of this times the vector r. Wait. Yes. So times but the thing is, instead of taking r, it's actually in the unit vector of r. So I'll call it unit r. So the unit vector in r is itself over r squared. So I should say, yeah, that's just like the vector r divided by its own length. It's scaled down. So whatever r is, so this is 10,000 kilometers. You want to get the same direction, but then you want a unit scale. That way it doesn't add any length for it, because this is the magnitude. This is the direction. That's what you want. And so if you want this particular magnitude and then keep the same direction, then you don't want any magnitude coming out from this. And so whatever magnitude r has, you cancel that out. And so only the direction stays.
Yeah.
That's the way I think about this. And so when you like put them together, you just get like a mu over r cubed and then times the r vector. Generally, we write these with like absolute values, but that just means the magnitude. So that way you don't mix things up. It's the magnitude of r cubed. And then you have r here, the vector. That's just the formulation. This is not even like showing how to solve it. Let me start you off now. Okay, so let me create a new state. Instead of calling z this, I'll call z as something else. So what we are like involved with, worried about, are our positions and our velocities. any higher derivatives aren't exactly important. So I'll start off with writing 4 states, and I'll write x dot, because that's a speed there, and that's a y and a y dot, speed on y. Cool.
Yeah.
Yeah. Okay. So the way my code is going to run, I say it on a high level, the loop, basically. The way the loop works is that, so you already gave it x dot, and you already gave it y dot. That's cool too. Dz dx, dz dt, sorry, how things change against time, is now this is x dot, this is y dot over there. We have this business, which we still don't know. That's x double dot somewhere there. And then we have y double dot here. Now the thing is, this dr squared dt automatically tells you x double dot y double dot, because it's a second derivative. You notice how the second derivative automatically depends on what r is?
Yes.
So if I wrote this in like proper like vectors and all out, right? So what I say is the r vector double dot, that's that is minus mu magnitude r. Okay, so this is the differential equation that they gave us. The way I can write this out in components is x double dot and y double dot equals minus mu over the magnitude of r. Imagine for each loop, we can solve for this magnitude each time. Each time we would recalculate what the magnitude of r is, because it might have gotten further, it might have gone closer. Yeah.
Yeah.
And then this r here is going to be just x and y, because that's just what r is. We defined that over there.
Yeah. Okay.
Okay.
Cool.
So the way what we can do is up the top. So the way we're doing it is like we're kind of taking whatever we had before, we change each of these, and then we repackage them. So then let me close that. That open bracket kind of looks weird alone. Anyway, so this x just shifts over. We just shuffle it over. Same thing goes for the y. The y, it just gets shuffled over. The x and the x and x double dot and the y and y double dot are related by this equation. So what we do is we pass it into this equation, pass this into this equation, and we extract x dot and y dot. There's a lot of arrows now. Let me do this with a different color. I just realized that. Yeah. So pass this in. We get out x dot, double dot, sorry, and y double dot. And once we solve that, then we can plug that in, and that's our second derivative. Then it'll automatically do our like little Euler integration by hopping across and stuff. The code does that by itself.
Yeah.
So the way I'll do this in practice is now, okay, so I still need to define some parameters as well. We'll do that later. Okay, so say for example, if I want to run this for half an hour, so that's 1800 seconds. Okay, so now I have initial x value and initial y value. So x naught, I said it was going to be 10,000 kilometers. This is 10,000 kilometers from the center of the Earth. Notice that this would be in km. Okay, so the initial y value, I just said it would be 0. And initial velocity, we need to give it a reasonable velocity. What's that? G mu on r squared, I think. No, what am I doing? Okay, I don't know what I'm doing. Let me open up the space textbook. This textbook is the same for space 1 and space 2. So
okay, cool.
This the same thing. Orbital mechanical engineering students. If you don't have a copy, yeah, I'll get you a link.
Yes, I do have one right here.
Oh, how convenient.
Yes, the book is right in front of me. Yeah.
It is the space textbook, because like, I kid you not, the lecture slides are literally screenshots from the textbook.
Oh my gosh, yeah. Then
like, if you
doesn't
notice
really
that you see
explain
the
heaps.
same, yeah, if you see the same, oh, you notice as well there's MATLAB scripts if you haven't seen it before.
I saw one at the back of it, but that's about it.
There's like a whole lot of MATLAB scripts, and it's like the first time,
Oh
if
my
you ever like
gosh.
thinking about solving any like problem, look through the MATLAB scripts, get an idea. Don't copy paste the MATLAB, because the MATLAB scripts it does the job, but it does it very poor. There's like a way better ways of
Okay.
doing it. Yeah, that's the way I think about it.
Yep.
Okay, give it a moment. I think it's somewhere here. That's a roadmap. Here it is. This is all our parameters. This is the mu that I was talking about. So this is GM automatically.
Oh, okay.
Okay, so for Earth, I'm looking at this 3,986,000, and I did everything in kilometers. So that makes life easy. So I need to also define mu somewhere. Do it in the function, and we'll worry about that later. Cool. We'll worry about that, yeah, later. That's cool. Okay, so an initial velocity. So what seems reasonable? Say if I'm talking about like something like circular motion, right? So then I think they gave us an orbital velocity. I remember how it was derived. It was like mv squared on r equals gm m on r squared, something like that. M's cancelled, r cancels, and then we just got v is equal to square root. Gm was mu, and so mu on r. Now we gave r as 10,000, and so mu was whatever number that was.
Yeah.
3,986,100. So that's 4. That's 39.86 meters per second, roughly. I'm just going to give it like 40 meters per second. A nice round number. So currently, my satellite or whatever, it travels at 40 kilometers per second. Sorry, not meters per second. That's a bit slow. Kilometers per second. Pretty fast. Yeah. So that's good idea to label your units. Yeah, you can label the others, doesn't matter. Anyway, so that would be y dot naught and then x dot naught. Have to put all your derivatives. So because you have a state of 4 variables, x dot, y dot, you need initial values for each of those 4. Yeah? No? Yes. So
yes.
We've defined as 0, y we started off as 10,000, x dot we should give as 0. And then y dot naught as 40 kilometers per second. Okay, so that means our initial state, x naught, y naught, x dot naught, y dot. No, sorry, the way I did it is x dot, y dot. So let's follow that same order. Let's put that over here. Looks better. Okay, so it's x naught, x dot naught, y naught, and then y dot naught. That. So from here, now I define my initial conditions. Works fine. My time span has been initialized, but I haven't defined my derivative. So I'll just call this gravity for now. So it's easy to understand what exactly we're doing here.
Yeah, not just Bob.
Okay. Yeah, it's not just Bob. Yeah. Okay. So, all right. So far, this Z already has 4 values. It has X as the first value. So that's the first value in Z. 1 comma all columns. And we have X dot. Can't spell. Okay. As the second value in Z. Again, I could like swap the order around, and like whatever order I did this, as long as you're consistent with it, the code will work fine. MATLAB doesn't care.
Okay.
It's just like, as far as MATLAB knows, it's just where the data is stored. And as long as you're like picking out data from the right row, then it will work exactly the same way. Okay, so y dot is the 3rd row, and then this is the 4th row. That's how that works. Okay, cool. So x dot, y dot. Nice. Okay, so now how do we work? So now first, we want to build up to this equation. So what do we need? We need mu, which we already inputted. Normally you would put this as a parameter or something. You don't want to define new constants inside of a function. Not exactly the best coding practice. Normally you would run them
Yeah.
as parameters.
Okay.
You could run them as global variables, but I don't remember how to do those, and I seem trying to look it up. Okay, so we got mu, but we need to get the magnitude of r, and so the magnitude of r is simply the square root of x squared plus y squared. So in 3D, this would work
Just
differently,
Python.
and I'm guessing you can get the analogy of how it worked there.
Yeah.
That r is equal to square root x squared plus y squared. Simple as that. Yep, x squared, y squared, and then
Okay.
now our derivative also has to have 4 positions. It needs to be x dot, x double dot, and then y dot and y double dot. Yeah. Okay. So we defined r. Now we actually need to build the differential equation. We've only built up like the stepping stones to it, but we haven't actually derived x double dot and y double dot, our final steps. So the final step is to just put this all together. So then, so let me just call it acceleration. The full acceleration vector is going to be minus mu on r cubed, bracket that in, and then that times xy. So yeah, so that's x, y, something like that, or x comma y, and then just transpose that. Whatever. They both mean the same thing. Yeah. So that's my acceleration. Then what I can say is I can say x double dot as the first value in acceleration, and then y double dot as the second value. That's one way you can do it.
Okay.
The other way you can do it is just automatically write it as x double dot and y double dot. Yeah. It really doesn't matter. It's only like a matter of preference there.
Okay, cool.
So the first value in acceleration, probably the first value and then all rows. And then the same thing for y, but the second. Something like that. And so x double dot we got there, got y double dot, we got all of this. Looking nice. Okay, so then when we plug this out, we get t, we get z. Now this won't be y, and so this business will be different. Let me comment that out for now, and I'll comment the rest of this out as well. So let me just run this. No errors. That looks nice. Imagine writing code and having no errors when you start. Wow.
Wow, well done.
Thank you. So yeah, so as you can see, that's our initial conditions, 1,000 kilometers, 0 y, 0 x dot, and then 40 kilometers per second as our derivative. We have z over here. And so this is how it started off. So this is our initial condition. And then each time period, it passed it on, it moved on to the next value. And so you can see like the time evolution for all of this. Yeah.
Yeah.
Okay.
Yeah.
You can see all of this, but then you obviously want to be able to like physically see it. So let's dissect this data. So Z is the whole four rows, and it's just unpack the whole state. The state itself is the vector of 4 variables. So each of these is the same state and how the state changes over time. So it's like, imagine bundling multiple variables into one package. That package is what you call the state. In our case, Z is the state. It's a state of x dot, y, and y dot. Anyway, so let's unpack this. So now, instead of y and y dot being those values, this is going to be the third value, and this is going to be the fourth value. And then for x and x dot, that's going to be the same thing, but the first and second values. X and x dot. First and second value. Something like this. Yeah. And so now I have x, I have y, and I have x dot and y dot. Looking nice. let me go plot my results. Now, instead of plotting how y changes against time, let's see how x and y change. And so you'll see the full orbit. When I run this, this is how it looks so far. This looks a bit sketchy. That's probably because of the way I oriented my axes. And let's see, have I forgot something in my code? No, that looks good to me. That looks fine. Yeah, that's probably just the way the axes are put in. So let me put axes equal. Axes. Or actually, I'll put this way, x lim. How did we put x limits again? It was, I think, negative 10,000.
Yeah, I can't remember.
I think it's something like this. Okay, where did it go? Oh, great. Okay, maybe I need to give it more time to run. 1 sec. Maybe give it an hour. I think it'll pop up. Do you see it anywhere?
Is it like,
wait.
look at the top right.
Top right. I'm looking at the top right. What am I looking at the top right? Oh, yeah, it's there. You're right. Okay,
Yeah,
never mind. It
it's
actually
like-
just shoots out. Yeah, so that's like, oh, it's gonna make a circle eventually. So now
Eventually,
ODE 45 is kind of accurate for smaller values, like as in like, you notice how we're dealing with huge numbers here. We have 10,000 and like hundreds of thousands over here. This is where ODE 113 comes in. So 113 works exactly the same way as ODE 45, except that it works better with big numbers, which works really, really well with orbital mechanics. So specifically try
okay.
113. So that way we get like more reasonable things. Okay, so maybe I don't want to do this as 10,000, maybe like 11,000. Okay,
And so like as a general rule of thumb, you should use ODE 113 in space courses as opposed to ODE 45.
Yeah, okay, I think the way this is working is, I think it's like shooting into infinity and it's just like, yeah, it just broke. Let me just run this again.
You broke MATLAB.
I broke MATLAB. Okay.
Oh no.
Nah, it'll be fine, don't worry. MATLAB doesn't have feelings to be hurt. Or does it?
True.
No.
Ooh.
Okay. But yeah, basically this is how it should work. Let me give it like a while later, like what even is that? That's 10 hours. Okay, I think it's also my axis limits. Let me just take out my axis limits for now. Okay, what is going on? I don't know what's wrong, but my code has died out. Okay, what is wrong here? Okay, but this is effectively how this works. Okay, my y is just building up to forever, which is not exactly what's meant to do. Somewhere there. But yeah, do you get the idea of how this works?
I think I am getting the idea. Yeah, it's starting to make sense.
Yes. All right. Actually, the easiest way that I can put this is that I just put acceleration as this, and then I can just put this as acceleration. So this is a constant now. So now times x dot x, sorry. And then this is times y. Yeah, that should work as well. No, it just doesn't want to work.
Wow.
Oh wait, I know what's the problem. It's moving too fast. It moves so fast as it escaped the Earth. That's what it looks like.
Oh, okay.
Yeah, so let me slow it down and then hopefully it will do better. So maybe like 15 kilometers per second looks like a nice round number. Okay, it seems to have gone a bit slower. Let me try something like 10.
Yeah.
Yeah, you can see it's being more round. Wait.
That looks better.
Gooder. No. 2 kilometers per second. Oh, there it is. There it is. Look at
Hey,
this.
oh my,
There's your
wow.
orbit.
Look at
Okay.
that.
All right. Now, if I
Wow.
enforce the axes to be equal, I think that should work fine then. Okay, that's it. My bad. Yes, equal. Okay. Doing this again. This is how the orbit now looks like. So I think it now, you see how it's varied a lot? This is generally because of numerical
Yeah.
errors. So
Oh.
obviously the code doesn't do this perfectly correctly because we're doing this numerically. Like there's
Yeah.
errors that build up. And so if you let it run for a long time, then these errors will like accumulate, and you may want to account for these or mention these in your reports. This is something you may want to worry about. This is another thing I wanted to show you as well, is if you make it too small, say for example, it's going 100 meters a second, your code will first run a very, very long time. You generally will also have this type of error. Failure at t equals whatever this is. Unable to meet integration tolerances without reducing step size. What that means is that it's approaching the center of the Earth or the center of whatever body it's orbiting, and it's basically like, just fell to oblivion. So you can see it started up over here and it just doesn't have the speed to maintain orbit. It just fell down and it keeps falling because there's no surface of the Earth here. And it just keeps falling, and then it just, crash.
Oh, yeah. Wow. Okay. Yeah, okay.
Normally this happens. The key telltale signs of this is that your code runs for a very long time and you get warnings or errors like this.
Yeah, okay.
And the quick fix that you normally have is just increase your initial velocity so that you have something reasonable. Yeah, it looks like it fell to the Earth now. Yeah, this fell into the Earth as well. Something like two worked fine, right? I can try one here and then one in the Y direction. Something like that. And then you notice that it launches at a different direction. Okay, just doesn't want to agree with me. Rip. I think I also let it run for too long as well. It'll run for an hour. Okay. This looks nice. So this still is falling towards the center of the Earth, but it hasn't hit there yet. But it looks like some very pretty orbits.
Yeah, it is nice to look at.
So this is the way generally like ODE solvers work. So what you would do with data like this is normally when you have your X and Y or Z as well, you start needing to transform coordinate systems. Have you guys dealt with coordinate systems yet?
He went over it, but we haven't really done anything with it yet.
Oh yeah.
Like in terms of orbital mechanics, yeah.
Oh, actually, yeah, speaking of, okay, so this is one of two ways you normally like model orbits. You can model orbits of multiple planets using the same model as well. Say for example, so this can be for like, I can call this like Sat1 for a first satellite. And so I have this model, or I can call this gravity actually. Let's call it gravity for now. Okay, so say for example, I can define a new thingy. I can call it T Z2, for example, equals, and then I can run this, same thing. But instead of this, I'll give it different initial conditions. And so I can get it to start from a different location, and I can get a second satellite going up. It gives it the same gravity model. So this is the model that we use. The time span should be the same, but then the initial conditions would be something different. So instead of this, I can say Z2 naught. So that is for the second satellite. So then, this, I'm just gonna like hard code this. Bad example, but you're not taking bad lessons, right?
No.
Good. Okay, so let me start this out from like maybe 15,000 kilometers away, and X dot, I don't know, make it like 2. I don't know, Y dot seems to work. Make Y dot go something like negative, I don't know, making up numbers now, 1.6. Oh, that's, sorry, that y is meant to be 0. And then y dot, make it like, I don't know, making this up now, negative, I don't know, 2, and I'll make this 1.5, 1. This should work fine. Okay. All right, so something like this.
Okay.
This satellite I might expect to escape. Yeah, Z2 naught, that's right. And so this is the second satellite here. So now I can unpack the other one. So I can go unpack the second satellite. So that's Z2, 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 Z2. And this is X2, Y dot 2. And then, yeah, that. All of that basically. And then I can run this and works exactly the same way. Now I have a Z2 and a separate simulation that just ran. So now I plotted X and Y. I can hold on and I can plot X2, Y2. And then you can see both satellites running at once now. There, that second satellite kind of went a bit fast and it just but you can see, let's see, what can I do? I can change its initial conditions to, what speed is nice. That's a bit too fast. So maybe something like a 0. Just go with that, 0. Okay. Still too fast. Wow, okay. How nice. How nice. Okay. Gosh.
Too speedy.
Way too speedy. Okay. I really don't like this code now. Wow. Code had one job. Wow.
Oh dear.
All right. So something like 0.2. Okay. If it falls into the earth now, gosh. Okay. My patience is wearing
Wow.
thin, but yeah. Wait. Okay. Oh, wait. Where is this starting and where is this ending? There's negative 15,000 here. It's X 0. Okay, what? This is mildly concerning. Okay, doesn't matter.
Yeah.
Anyway, but you get the idea, right?
Yeah.
Right.
Yeah.
Okay.
Yes, I do.
Okay, I think the way this is actually working is that it's too slow.
Oh, and it's
Okay.
going into the
And it's
earth,
going
and
into
it's
the
like,
earth. Yeah,
oh,
it's about how you diagnose your data as well.
yep.
Gosh. So y is going negative, x is in the negative position as well. That makes sense, right? X y dot. Yeah, that should make sense. I don't know why this is not working. Give it the same speed as the one before. What was that? Y naught is, wait, y naught doesn't even need to be 2. That doesn't do anything. Y dot naught is 1. Make that negative 1. And then like make it negative 10,000.
Yeah, shrink it a
That
bit.
it's like exactly the opposite. Okay, my code
Wow.
be weird. Oh wait,
Why?
falling.
Why
still
is
falling.
it like?
Wait, X
Oh
and
my
Y are
gosh.
both defined as 15,000. This is sketchy. This is some sketchy code here. Okay, what is this? No. I got it. I got the problem.
What happened?
I've got to transpose these.
Oh.
So when I forget to transpose them, it joins 2 points in the line or something like that.
Okay.
So it joins them together. And so that's why it looked weird.
Oh, yikes. Okay.
So many errors that can happen. Okay, what happened here? Oh boy. See, mistakes like this just keep carrying on.
Oh no.
I'll call this T2 so that way they don't get mixed up. Because
Smart.
each time it runs a simulation, it runs it. This is the sort of thing you're looking at.
Whoa. Okay.
It's because I forgot to hold off as well.
Oh.
Otherwise, it keeps holding on from previous simulations.
Oh, okay. And that's why there's so many colors going on.
Yeah, another thing as well that I should do is that. That's also good practice.
Okay.
Okay, this is what we're looking at. Look at this. This looks like
Okay, that
perfectly
looks a bit
symmetrical
nicer.
because they're
Yep.
starting from like
Oh.
opposite positions and like they have about the same velocity. I can speed
I
them
love
up a bit.
that. That's
know,
like
right?
art.
This is such art. If this is like, yeah, why do an arts degree when you can do space? Nah,
MATLAB.
kid. But yeah, so this is the sort of thing that you're looking at. Yeah.
Yep.
Okay. So this is like, yeah, if you, because I think from memory, space assignment 2 was you modeling basically was it assignment 2 or assignment 3? One of those. One of them was modeling multiple satellites going around the Earth. Another one of them was basically a trip from Earth to Mars.
Oh.
If you're planning a trip from Earth to Mars, you want to map where Earth's position is and Mars's position compared to the sun.
Okay.
So, you know, it might be convenient to model both planets around a sun or something like that.
Oh, okay.
You know, something to think about. How convenient that one of them is blue and
Yeah.
one of them is red. Huh. No, okay. Coincidence? I don't think so.
Wow.
No.
Oh my
Yeah,
gosh.
so this is the sort of thing that ODE solvers do. Does this make sense? Do you
Okay.
have any questions for me, or this took like an hour? Gosh, just like a lecture. Gosh. No.
Well, I just really appreciate your thoroughness and like your willingness to help me, because this is really helping a lot, like a lot.
To be honest,
Yeah, I
though,
appreciate it so
like
much.
they don't go through ODE solvers in space, and I know quite a few of my friends, they just did things with Euler integration, making a loop, and that just makes their
Ooh.
code run way longer, and it makes just way more
Yep.
thinking as well.
Yeah.
It's literally like ODE solvers is first model how long you're running and then your initial conditions. It's like anything more than that, you're thinking too much. That's just
Okay.
the way I think about it. So it's like as long
Yeah.
as everyone is able to get on this, at least on the same like level there, it makes it so much easier, that much easier to pass space.
Yeah. It's
All right.
definitely. I'll definitely be using that in like all my assignments now.
So yeah, so make sure you get the idea of like states and stuff like this as well. If you want, I'll just like send this PDF as well.
Yeah, that would be really helpful. Thank you.
All good. Okay. All right. Yeah, if there's nothing else, then we'll wrap up. Yeah.
Okay. Yeah. And
All
yeah,
right.
thank you again. Like really appreciate it a
Also,
lot.
if you have any questions, don't be afraid to ask. Yeah.
Okay, so like I wouldn't be bothering you again by
No,
like asking something.
It's fine. It's fine. And I have it.
Okay. Cool.
All right.
Yeah.
Okay. In that case, yeah, take care. Have a great night and good luck for your space assignments.
Oh, thank you so much. And you too.
Thank you.
And I'll catch you later.
See you soon.
Bye.
Bye.